Good morning, everyone. I'd like to, first of all, thank TRA for organizing this event where different companies and people can come together and interact with a wider audience about different technologies. Today, the topic is open networking and SDN, and I will take you through this session. I work for Dell EMC, and I have about 20 years of networking experience. I've been with Dell EMC since 2012. I come with a lot of multi-vendor experience across different customer segments in enterprise, service provider, across Middle East and Africa. Academically, I am a computer engineer. I have a bachelor's in computer engineering, and I have done a master's in business management from the University of Strathclyde in UK. I have several hobbies. Some of them include motorbiking, which is my favorite. I love traveling, reading, and exploring nature. That's my other side. That's the things I do when I'm not doing networking. So staying on the topic, today we're going to talk about open networking and SDN. So when we look at networking, we see that very little has changed in the last 20 years from a networking stack perspective. We have the same protocols. We've just added more protocols to the stack to solve different problems. To do a L2 stretch, we have certain technologies. So that's how we have organically evolved. But nothing that has prepared us for the cloud era that we are in. The stack is very much built with the client-server era in mind. And since then, it has undergone very little change. So what is available to us to actually prepare our networking stack for the cloud era? And that is what we're going to talk about. So let's look at all the different challenges that we have in today's networks. So if I divide this into edge, core, and cloud, at the edge, we have very complex and expensive technologies that we use today in the edge. The challenge is MPLS has become the standard technology for wide area connectivity. However, that is also very expensive. It can be complex. And we have newer technologies that are software defined today for the WAN. In the core, we see that most of the technologies that we have are proprietary and closed. And that it does not help you be agile. It limits you, and it ties you into a certain proprietary technology stack. And that is what we are trying to change. That is what we are trying to change with open networking, trying to make networking more open. Now, we are also at an era where everybody is looking at the cloud. We are trying to digitally transform ourselves, and part of the digital transformation also means that the IT has to be transformed. And when we talk about IT, networking is the plumbing that holds everything together in the data center. Now, how do we change that? And when we talk about cloud, everybody is thinking of, do I move all my workloads to the cloud, or am I going to keep certain workloads on-prem and certain workloads in the cloud? And if I'm going to do that, how am I going to have a common set of policies to manage my network that is on-premise and my network that is in the cloud? How do I achieve all of this? How do I move my workload seamlessly from my private network on-prem to the public network, which is in the cloud? And for all of this, I need a network that will give me all these capabilities, that allows me to do everything in a very simple, easy, agile manner. And for that, I need some level of automation to achieve that. So when we talk about open networking, I have basically divided this into two phases or eras, and I like to call it Open Networking 1.0 and Open Networking 2.0, because it has been a journey when it comes to open networking, and I will take you through this journey and I'll tell you what has evolved and how this has evolved over time. So to talk about open networking, I would first like to talk about how computers evolved, because that is something that we all relate to very easily, before I take you to networking and make that comparison and make you understand how this applies to networking. So when we started in the compute era, we had a mainframe model. Every vendor made the hardware and the operating system. So it was tightly integrated. So if you looked at some of the vendors that made mainframes, IBM, HP Arc, Sun Solaris, Digital, all of these companies made their proprietary CPUs, all right? Spark and RISC, Alpha, all these different proprietary CPUs that were there. And then you had all the proprietary operating systems. Every vendor had their own operating system that ran on their specific hardware. So you had the hardware, you had the operating system, and these were tightly integrated. So you had proprietary CPUs, and then you had proprietary operating systems. Sun Solaris with Spark workstations running Solaris as the operating system. Same thing with HP Ux. You had their own hardware and then the software. And so every vendor was doing this. Even Mac, at one point, they had their Mac-based proprietary CPUs, and the Mac OS was proprietary that ran on top of it. Now, the problem with that is it created a problem for application vendors. Applications had to choose, am I going to support my application on this operating system or that operating system? And then customers were left with a limited choice of applications when they chose their operating system. That did not allow for customers to have the choice of different applications. So most of these proprietary architectures also meant that you need very proprietary tools to actually manage this ecosystem. So that was the limiting factor when it came to a mainframe approach, a mainframe architecture approach. So compute evolved from here, all right? From this proprietary mainframe model, it evolved to the x86-based era. In this era, x86 as an architecture became widely adopted. Intel led with the CPUs that they built. Intel, AMD, those were the companies that built these processors. That allowed for other standard operating systems to come in because now you disaggregate the hardware and software. So companies like Intel and AMD made the processors, and the ones who built the servers and the x86 servers, companies like Dell, HP, Sun, all of these companies now started just buying the chipsets from a third-party company like Intel. Nobody manufactured their own CPUs. Dell, HP, Lenovo, none of them manufacture CPUs. They all go and use the CPU that is manufactured by Intel or AMD in their servers. That made the architecture more open from a server perspective. So when you have a CPU spec, you could then choose, do I want to buy this from Intel? Sorry, I will not go and buy Intel. I do not expect Intel to manufacture the server for me, but I'm just going to buy a server from any of the vendors based on a certain Intel platform, based on whatever they offer in terms of hard disk, or do I want a SSD-based disk, or do I want this much of memory? And then I look at the kind of support I get from the different vendors, and then I make that choice. Do I want to buy the server from vendor X or Y? Now, what this allowed is it allowed for different operating systems to be standardized. So you have Windows, you have Linux, you have all of these different operating systems now working on the different hardware platforms. And that also helped the application ecosystem to evolve, because now you had more choice of applications that could work on any of these different operating systems, and hardware was no more the limitation, because now you've made a hardware standard. You can put any operating system. You've disaggregated the hardware and software, and the application stack is again disaggregated. So, and then the orchestration, automation, etc. for distributed computing became very open. This really helped the applications develop and evolve the way you see today, the way physical hardware has become virtualized. So today you have virtual machines. We no more talk about bare metal servers running a single application workload. You could run several virtual machines. You can have containers. You can have all of those on a single physical hardware. So that is the beauty of this open standard approach that evolved in computing. Now let us go and look at what is the architecture that we have for networking. The traditional network architecture for many years has been proprietary ASICs. So most of the features and functionality in a networking switch actually comes from the ASIC. If you don't have that feature in the ASIC, I cannot expose it in my operating system so that you can go and configure and do things, because you want to do it in ASIC because it becomes much more faster. Those networking functions that you want to do has to be in the ASIC, in the hardware, so that it becomes very fast. You can have nanosecond throughput and all of that because it is built, these features are built into the ASIC. Every vendor for many years has made his proprietary ASIC. He has made his own operating system, which has hundreds of protocols, proprietary architectures, and then they'll come out with management tools that will help you manage all of that they've built. So that is the approach that has been prevalent in the networking industry for many years. So if you don't have the choice like you have in compute, where you just buy a switch from any vendor and everybody is based on the same ASIC, you didn't have that for many years. All right. So that was the traditional approach that everybody took. Now that changed with the advent of merchant silicon. Now here is where I need to explain to you what is the difference between custom silicon and merchant silicon. So the ASIC inside a switch, when it is proprietary and it is called custom silicon when it is manufactured by the same network vendor for use with only their switches. So then it's proprietary, because then it's not something that they sell to everybody else. They manufacture this ASIC that will work only with their switches. That is custom silicon, and it is very proprietary in nature. Merchant silicon, on the other hand, refers to off-the-shelf ASICs, where instead of a vendor-developed proprietary ASIC, you actually manufacture, your sole focus is to manufacture the ASIC, and you sell that to different switch vendors. So Broadcom is one of those leaders, is by far the leader in merchant silicon, which is widely adopted by all the networking players. There are other chip manufacturers like Barefoot, Centric, Marvell, Cavium, Innovium, Mellanox, Intel as well. All right. So they're all into ASIC manufacturing. Now, with the advent of merchant silicon, many of the mainstream networking vendors moved away from manufacturing their own proprietary ASICs. They started adopting merchant silicon, and they started manufacturing their switches using merchant silicon. Instead of putting all the R&D dollars into manufacturing the ASIC and making it very proprietary and making it work only with their operating system and with only their switch, vendors started adopting standard merchant silicon. Now, and you will see how popular this has become. In 2018, for example, 56% of the Ethernet switches that were shipped were based on merchant silicon. And by 2022, it is estimated that 63% of all Ethernet switches that will ship will be based on merchant silicon. If you look at some of the recent announcements in the last year plus, where everybody started talking about the 400 gig switch, one thing you will notice is that everybody has based their 400 gig switch platform. They have based it on merchant silicon from Broadcom. And again, in Broadcom, when you start looking at it, they have different chipset families. They have the Trident chipsets and they have the Tomahawk chipsets. The Tomahawks are mainly, more intended for, low latency throughput, and switches that use the Tomahawk chipsets are usually meant to be in the spine layer. The Trident chipsets are more feature rich and meant to be in the leaf layer of a spinal leaf fabric. So you see that all the big vendors have announced their 400 gig switch, be it, all the top 3-4 vendors have announced their 400 gig switch platform based on merchant silicon, and that is from Broadcom, which is the most popular, merchant silicon vendor. So that shows that there is wider adoption. So the market has changed. At least the hardware has become standard. All right. So at least the first stack, which is the hardware, has become standard. And because the chipset has become standard and widely adopted, this also gave rise to an industry of white box switches. Now, what is white box switches? White box switches is where the white box switch manufacturer uses merchant silicon in his switches. He doesn't put any operating system on the switch because his sole objective is to make a standard white box switch. Just like you have white box servers, you have white box switches. He does not have a brand. He doesn't sell it like Dell or HP or Cisco or anyone. What they do is they are into the wholesale market. They manufacture these white box switches so that large companies, service providers like or cloud providers like Amazon, Google, Facebook, all of them. I mean, there are also a lot of service providers who use white box switches. So they take these switches from these white box manufacturers, they put their own operating system, and Linux has become the default standard operating system that is being used in switches. Now, everybody takes some version of Linux and they actually scrub it, they use the kernel, they modify it, and they use it for their switching purpose. And that is what these large cloud providers have done. They've all adopted white box switches, and that has reduced their capex, their initial investment in buying a branded switch, by about 40% at least. So that is the kind of benefit they see by going white box switching. They also move away from proprietary architectures and operating systems and all of this. So companies like Facebook, once they started building their massive data centers, they learned a lot of lessons by actually building these large data centers based on white box switches and operating systems and the spinal leaf architectures that evolved in those data centers. They wanted to take this learning in these data centers back to users so that everybody could benefit from their experience, and they could make networking and data center more open. So they wanted to actually start a non-profit organization, and they were one of the early founders of the Open Compute Forum. So Compute Project, sorry. So Open Compute Project was founded by Facebook. It was an internal project in 2009 called Project Freedom, and later in 2011, Facebook shared its designs with the public, and along with Intel, Rackspace, Goldman Sachs, Sun Microsystems co-founder Andy, they launched the Open Compute Project, and which was later incorporated as the Open Compute Project Foundation. Facebook, from their experience in their data centers, they realized that there was at least 38% more energy efficient. They realized that the new data centers were 38% more energy efficient to build and 24% less experience to run than the company's previous facilities, which were based on branded equipment from mainstream vendors. And this led to greater innovation, etc. And this is something that they wanted to share back with the world community, so that people could learn and we could evolve and have more innovation. And along came Open Compute Project, OCP. There are a lot of other members who joined, after this was founded. There are a lot of companies. We'll talk about it. And today, since our topic is open networking, there were several projects that they embarked on to make compute more open and to bring in more innovation into the data center. And in networking, there were several projects that you will see there. And I'll talk about two of them today. One is ONIE and one is the Sonic. So the project ONIE was a project that was based on creating a small operating system, all right, that will allow for disaggregation of hardware and software. So we looked at the traditional networking architecture earlier. We said that this architecture stack basically has proprietary ASICs, proprietary operating system, hundreds of protocols, and proprietary architectures and management tools that bring it all together. So that was the traditional approach. And this traditional approach where you have proprietary ASICs with an operating system that is again proprietary, is something that creates a vendor lock-in, and this makes it proprietary, and that is what we are trying to change with open networking. So under the networking projects that OCP undertook, one of the key objectives was hardware software disaggregation. So the hardware is already standard when they start using a merchant silicon. Now, how do I disaggregate the hardware and software? That was one of the key objectives that the Open Compute project endeavored to do. So as part of this, they set out to develop something called ONIE, which is Open Network Install Environment. It was an initiative from the Open Compute project, and it was basically to define an open install environment for bare metal switches, so that normally when an operating system comes up, it bootstraps. There's a bootstrap loader that will actually recognize all the device peripherals, etc., and then come up, initialize, and then the operating system gets loaded. So that part is what ONIE actually, that is the functionality that ONIE basically does. ONIE actually allows us to actually bootstrap and bring the switch up and gives you some sort of it's not a hypervisor, but it gives you some sort of an abstraction, from the hardware, so that the operating system can then be loaded on top of it. So that was beautiful. So this allowed for customers to buy hardware from vendor X, and they could go and buy the operating system from a vendor Y. This gave customers the choice. It gives different, it gave rise to different network operating systems to evolve, so that you don't have to necessarily manufacture and make the entire stack of hardware, software, etc. You could focus your expertise on developing a network operating system that would run on any switch which runs the ONIE bootloader. So there were many founding members to this: the Acton, Agema, Big Switch Networks, Broadcom, Cumulus, Dell, Penguin Computing, Quanta. They all contributed to this Open Compute project. And that is how, they all came together and they developed something called ONIE, which was given back to the open community. There was several companies that adopted it. Dell was one of the early adopters of the ONIE operating system, ONIE bootloader. So all the switches that Dell manufactured after that came preloaded with ONIE bootloader. This allowed Dell to actually put in their own operating system or give customers the choice of loading any third-party operating system other than their own. So that made this disaggregation of hardware and software possible. ONIE really realized that dream of disaggregating hardware and software, so that this ecosystem of operating system vendors can flourish. New operating systems can come in with a lot more innovation and give customers the choice to actually choose between different operating systems based on their workload needs. Every network is different, every customer's environment is different, and hence they could choose which path they want to go when it comes to automation, because each operating system comes with a different type of an architecture, different innovation, and that gave customers the choice. So let's look back at what changed between traditional networking stack and the open networking stack. So if you look here, you have in the traditional networking stack, you had proprietary ASICs. Today, most of the vendors, we said almost 60% plus, use merchant silicon. Most of the vendors earlier had a proprietary operating system. Today, in the open networking stack, you can use merchant silicon, you can have any open standard hardware with ONIE, and have any network operating system running on top of those switches. So, and then you can have any optional overlay controller. Okay, so in networking, the switching hardware is called the underlay network, and that runs its own operating system, and that is one part of the network solution. And then you have something called an overlay network, which is software defined, which can run at the host. So you're basically taking the networking intelligence and distributing it at the host layer, which we call overlay networking. So you don't have to really come down to the physical underlay network to make networking decisions, the overlay controller can, take those decisions right at the host. So you have a choice of different overlay networking controllers, and then you can use any standard orchestration and automation tools. Now, you don't have to go back to the same vendor to give you a management platform and tool to manage the entire stack. This is the beauty of open networking. It allows you to have the best of network operating systems, the best overlay controllers, the best of orchestration and automation tools that actually meet your requirement, as because every network environment is different, every customer requirement is different. Depending on the vertical, their requirements can again be different. So this open ecosystem allows for all of that to evolve and happen. Now, we talked about how networking evolved. We talked about ASICs, custom versus silicon, and we saw how we got to white box switches. And there were switches that vendors like Dell, who adopted the merchant silicon with ONIE and embarked on the open networking journey. Gartner calls those switches bright box switches, just like you have white box. These are branded white box switches. These switches, they run ONIE bootloader, allowing you to actually load any different operating system on top of it. But they are branded because they bring in more support, capability, etc. So that is one of the things that happened. So we spoke about all of this. Another thing that evolved is because of the popularity of merchant silicon and adoption of merchant silicon and the adoption of these, in the ONIE, etc. Another thing that changed in the networking industry is the evolution of spine and leaf architecture. So before, you had multi-chip architectures. In a chassis-based switch, you had a supervisor module, all right, that controlled the different line cards through a backplane, because all the line cards were connected to a backplane, which helped the line cards talk to the supervisor, and the supervisor would, help all the line cards function. And to increase the speed and latency, we also had some special chipsets that were put on each of the line cards to help these line cards behave better, to give you better performance, to reduce the latency, etc. So that was the traditional architecture where you had multi-chip architecture. Now, with the advent of merchant silicon and the popularity and the learnings that came from all these large data centers, everybody realized that chassis take a lot of space, power, and cooling. And in large data centers, this was one of the biggest challenges that most of these cloud providers and large service providers faced, because any chassis switch does not come, in a single form factor, 1U form factor. Most of them are 4Us, 6Us, 8Us, 14Us, etc. Today, you have a 1U switch that can have 32 400 gig ports in 1U. That is the density, that is how the form factor is reduced. So you have much more powerful switches that can come in a single 1U form factor. Now, the challenge is, how do I provide the same functionality that I have in a chassis? Because in the chassis, you have supervisor with several line cards. Most of the line cards started with 24 ports. Later, they became 48 ports. So that is what we saw in line cards. So how do we take this into a more scalable architecture? And that is where a lot of companies started looking at spine and leaf architectures, all right, where the spine switches are like the, fabric card, all right, or like the, interconnect. And leaf switches are like the line cards, all right, and all of these can be 48 port line cards. You can have two of them for high availability. So you have two leaf switches, which are 48 ports, and then you have a layer of spine switches. It can be two, or it can be more than two based on the requirement. And every leaf switch connects to all the spine switches that are there. So this way, every leaf switch connects to every spine in a full mesh topology. The spine's function is basically to make sure that they provide connectivity to all the leaf switches. So if leaf switch 1 wants to talk to leaf switch, let's say in our example here, we have, let's call this leaf switch 1, 2, 3, 4, 5, and 6. So if leaf switch 1 wants to talk to leaf switch 6, they are just one hop away, And then in spine and leaf architectures, in large spine and leaf architectures, usually they dedicate 2 leaf switches to act as what we call border leaf switches. These border leaf switches can then have all the services that is required for that fabric connected to it. That could be load balancers, that could be firewalls, etc., etc., etc. Now, this spine and leaf architecture can be SDN based. It can have an external controller that controls the spine and leaf fabric, all right? Or it can be a non-SDN based spine and leaf fabric. Now, this fabric architecture is called a CLOS, C-L-O-S, clause-based architecture. It's borrowed from a famous scientist or who actually developed a hierarchical 3-tier architecture for the voice world, and this clause architecture is borrowed from there into networking, and that's why spine and leaf architectures are called clause architecture, C-L-O-S. So that is the architecture that we see today. So instead of large chassis switches, most of the vendors are moving away from that to build a spine and leaf architecture. Now here, in this example, we have 4 spine switches. If each switch was 1 terabit, with 4 switches, you have 4 terabits of switching capacity for the fabric. So that is how you determine the switching capacity for the fabric. Now, what is the advantage of having more than 1 spine switch? Basically, that allows you to have high availability or resiliency in your network. And also, you can have more switching capacity. And why is that? Let's go back to the leaf switch. If a leaf switch is 48 ports, all right, and let's say every port is 1 terabit, and 48 ports will mean the switch is capable of 48 terabits of throughput. Now, on the uplink side, so that is the downlink, right? That's where all the compute workloads are connected on 1 gig. And 48 ports means 48 ports. Everybody at 1 terabit will mean 48 terabits. You need to make sure that it's a non-blocking fabric, or you start determining what is the oversubscription that I will have. I will have 1:2, 1:4, 1:6. You can determine your oversubscription. So when you try to achieve non-blocking throughputs, 1:1, so that is where you will sometimes end up requiring more than 2 spine switches. So it depends on the products you choose, depends on the architecture. Sometimes you can do everything with 2 spine and many leaf switches based on a fabric requirement. Another thing is the size of the fabric. Sometimes a spine switch only has 32 ports. So that means in the 32 ports, you can have 32 leaf switches connecting to each of those spine switches. And once you run out of that, and if you want to have a bigger fabric, that's when you think, okay, maybe I need a bigger spine switch, or I add more spine switches, etc. So these are design aspects that determine how you build this spine and leaf fabric. So that is how chassis evolved, and we have spine and leaf switches thanks to the industry moving to merchant silicon, and that becoming very popular with the cloud providers. And those learnings that we have from those large cloud providers is something that gave rise to spine and leaf fabrics that are very energy efficient. They are usually 1U or maximum 2U, depending on the density of the switch and the ports that it has, and they are getting bigger and better. We started with 32 port 40 gig. Today we have 32 port 100 gig, and we have also seen 32 ports of 400 gig in a 1U form factor. So that is how this space is evolving with 1U switches. Everybody's trying to keep it as small from a footprint perspective, and they're trying to lower the power, because large chassis switches normally took 1,400, 1,500 or 3,000 watts of power. These switches are smaller. They take hardly 200, 250, 300 watts of power. So all of these are the benefits of power, less power, less space, and less cooling requirements for the smaller switches. Now, with all of this coming together, I also wanted to talk about the open networking architecture that is evolving. So hardware has become kind of open and standard. And then you have different operating systems being sold separately. So you have, for example, IP Infusion, Big Switch, Cumulus, Pluribus. All of these different operating systems have evolved separately. So these operating systems can be sold independently of the hardware. So you can buy a branded white box or a white box switch on which there is ONIE loaded, and then you can choose any of these operating systems from that are available. You can also go with Open Edition, OS 10 Open Edition, Open Switch, or Sonic, which is another project that is there with OCP. Or you can go with FRR routing. You can go with Bird, Quagga. So all of these choices are available to you. So you can build your network based on your requirement. Either you can go with hardware from a white box vendor or a bright box vendor, and then you can choose any operating system sold by any of these vendors for which you will have to pay. Or you can go with an open ecosystem, community-driven operating systems like Sonic, or you can choose Bird, Quagga, etc. So you have all of these different choices, and that is something that a lot of cloud providers and service providers do. Then comes the automation piece. And in the automation piece, you have Open Daylight, you have ONOS, SaltStack, Puppet, Chef, Ansible, all of these different pieces that can actually help you with DevOps-based automation. Then you have the orchestration piece, which is, you have OpenStack, you have OpenContrail, Midokura, Jenkins, Terraform. Then from telemetry perspective, you have Telegraph, InfluxDB, Grafana, CollectDB. There are so many choices. So you can actually build a network based on total open networking architecture and ecosystem. So you have a lot of choices there. Each of them bring different capabilities, and you can have a very resilient, highly available network based on a very open-based architecture. So next topic. So I talked about open networking 1.0. I will come to what is 2.0. But before that, I want to touch upon software-defined networking. Now, software-defined networking is about automation. My takeaway for software-defined networking is what does it enable? I mean, why do you want to go software-defined? The icing on the cake is basically automation to enable you to go towards cloud. So software-defined networking is about automation to enable cloud. Now, let's look at what we are most familiar with, right? Automobiles. All of us drive, most of us drive. We have cars, we are very familiar with it. And most of the accidents are caused by what? Is it mechanical failures? Mechanical failures is basically 3% of most accidents. What causes most accidents is human error. 94% of most accidents are caused by human error. Now, how do you eliminate human error? And that is the challenge. And same thing, same has been the challenge in the automotive industry. So what people are trying to do is evolve from manual cars to automatic cars, and then we have seen self-driving cars. The end in mind has been to eliminate the error-prone manual process and give that time that you focus on driving to more productive things. Before, you had to always watch and shift gears, hit the clutch. Then came the era of automation, where you have automatic transmission. So you had a better driving experience because now you did not have to be worried about shifting gears, etc. That relieved, gave you more time, helped you relax, made your driving experience better. And with self-driving cars, you have reached a different level of automation where everything happens on its own. There is less, accidents because of this, and that is where we are trying to go with self-driving cars, making them intelligent. They actually have 360-degree view. They can see everything. They're programmed to actually take action when evasive action based on certain scenarios, etc. So we're trying to build more intelligence into these cars and make them safer, better, etc. So that is what the automotive industry is trying to achieve. Now, if I take this back to our networking world, I would say First, the manual transmission that we had in the automotive world is very similar to the box by box CLI approach, which is legacy and traditional. And that is something that we still follow today. And that is okay when we have small networks and small environments, then it is fine. All right. There's nothing wrong with it. But then as the network grows, and today I told you people are moving away from chassis based architectures and into spine and leaf architectures. Now, when you move away into a spine and leaf architecture, the new problem that you have is, okay, I have so many spines and leaves, and I need a simple way of configuring all of these switches. I need less touch points to actually configure and manage them. And that is where the evolution to the automation came in, and different vendors started coming out with a fabric manager of sorts, zero touch provisioning, a centralized GUI. So you just connect all the switches into a fabric, and then you have a management network where you have some sort of a controller or fabric manager that will automatically provision the entire network and bring it up. So that is another approach of automation that evolved. So yeah, you have the manual, which is not automation. It is a command line interface, box by box configuration. The first step of automation is a fabric based manager, that allows you to automate, the spine and leaf fabric, so you can actually configure and bring up your network. The next level of automation is basically where you have total automation in the data center for server, networking, etc. And that is a DevOps approach to networking. In this DevOps approach, you use tools like Puppet, Chef, Ansible, SaltStack, etc. to actually allow you to do the configuration management, where you have templates that are put into these tools, which will push all of that configuration to the switches. So you have zero touch provisioning using these tools. And then you can have an orchestration layer on top of it that orchestrates different things, not only the configuration, it can do simulation, testing, all of that. It brings in a lot more capabilities. So I want to quickly, since Dell is one of the leaders in open networking, I just want to talk about the different operating system approaches that a leader like Dell does. So here, Dell has OS X, which is an operating system that they have, and they have another operating system called Sonic, which is an community-driven operating system. They have another operating system called Cumulus, Big Switch, and then we have Pluribus. Now, when you look at a vendor like this who offers you different choices of operating system, you're often confused and wonder, why are there so many different operating systems and what is the benefit for a customer? Now, broadly, we can throw these different operating systems into two buckets: non-fabric based and fabric based. What I mean by non-fabric based is these operating systems support the box by box CLI approach. All right, you can go into each box and configure them independently, or they have a fabric manager of sort where you can actually go into that fabric manager and then configure that entire spinally fabric. With OS X and Sonic, it supports both the approaches. In the case of Cumulus, it's a non-fabric based solution, and you can only do box by box, or you have to go DevOps based approach, which I'll talk about in just a minute. Big Switch is a fabric based approach where they have a fabric manager, they have an SDN controller, which allows them to configure that fabric. Or Pluribus, in the case of Pluribus, they don't have a centralized controller from where you control and manage all of this. They actually take the approach of distributed control plane, where you can go into any switch and configure the rest of your fabric. Recently, they also have brought in a fabric manager that can actually manage the whole switching fabric from software, which acts like a fabric manager. I told you about the underlay network, and these all form part of the underlay, where you have operating systems, and all of the operating systems run on these switches, which form part of your underlay. In larger networks, you have something called overlay network. NSX is one of those popular overlay networks that are used. And then you have the orchestration and automation layer using a combination of OpenStack, Ansible, Puppet, Chef, etc. So in this approach, you do all the configuration management not from any fabric manager, but you will use the Puppet, Chef, or Ansible and OpenStack to do the orchestration, and any of these to actually do the configuration automation. You'll have templates from which are pushed to the switches, and that is how the switches get their configuration. Another approach is you don't use out-of-the-box automation tools. you actually go and build your own, what we call continuous integration, continuous development pipeline. So here you will use Python and other scripting tools to actually build a script. When you run a script, that script will actually go and zero provision your network by picking up the configuration templates from one of the tools like Ansible, pushing it to the network. It can actually simulate, it can build, it can continuously evolve. You can add pieces of code to the configuration and build your configuration templates. There can be a different configuration template for border leaf, different for workload leaf. You can build it, you can test it, you can keep adding, and that's why we say continuous integration and continuous development. You can actually have a simulation of the network. Once you have simulated, tested it, you can push it into production, and then you can take it into production. So this is the most popular open networking vendors architecture. Like Dell has switching platforms with ONIE. They give you a choice of different operating systems. One is OS 10, which is their own, or any third-party operating system that you can see there: Pluribus, Big Switch, Sonic, and Cumulus. They also have an open approach where you can use the open edition of OS 10, which is available to the community. You can actually use Bird and Quagga on top of it. You can actually just buy the hardware from Dell and use any of the different community-driven operating system approaches like OpenSwitch with Bird and Quagga, or Sonic, that will enable you to run your network. The advantage of open networking is it gives you an array of choices. It gives you an open architecture. It allows you to repurpose hardware and software. It allows you to standardize on hardware. You can reduce your total cost of ownership and brings you investment protection. We talked about everything that is to do with Open Networking 1.0, and I talked about SDN, and I talked about automation, which is the key factor in SDN. Now, we talked about all these different operating system vendors, and what happened is all these operating system vendors went through a consolidation, of some sort in the industry. Different larger vendors picked up the smaller network operating system vendors, and the main intention of this whole path of these network vendors were that they could work on any open hardware. But with the acquisitions happening and consolidation in the industry, a lot of the smaller network operating system vendors were bought out by larger vendors. That took us back to where we started. Because of this consolidation and them going into larger vendors, the approach is some of them have kept it open, but some of them have made it proprietary. They've taken it back to a proprietary model where that operating system is only supported on their switching stack. So the Open Networking 2 is basically the emergence of Sonic as a community-driven network operating system. So here, you don't have the fear that the network operating system is going to be bought out by somebody, but the fact that this is an open approach, it's community-driven, and so there is no fear that somebody will come and buy it. And this is widely supported by different vendors today. There are most of the mainstream network vendors contributing to this. Dell, Cisco, Juniper, all of them are contributing to this. And Dell has even gone one step ahead and announced an enterprise version of Sonic that will be supported, by Dell. So open community version of Sonic is also supported. So that is the emergence of Sonic. And this, I believe, is Open Networking 2.0. I'm open for questions, Q&A. We have 10 minutes to go. So if there are any questions, I'd like to answer them. I'm not able to. Are there any questions yet? Please feel free to drop in your questions on the, so we can actually answer them. So I'll wait. And if any of you have questions, I'm more than happy to answer. I had to speed up a bit to catch up the lost time so that we have time for question and answers. I'll be here till 12 o'clock, guys. I mean, it's 11:51, so we still have 9 minutes. Please feel free. I mean, this is a forum that is created, for learning, so that different people from the industry can come and talk about different technologies and different topics. And this is to create this environment of learning where we give back to the community, and we can enable people. So please feel free to raise your questions. We are more than happy to answer all of them. I also want to tell you, for the assessment, there will be questions and answers. So if any of you like to take the assessment, there will be an assessment as well, which is going to be based on what you just heard. Okay. So since there are no questions, I'll do a quick recap. Today's topic was open networking and SDN. And what I talked about was about how networking has evolved. We started with traditional proprietary architectures, where you had a proprietary ASIC chip, proprietary operating system, and a proprietary stack, and how that evolved, moved away from a proprietary mainframe type of an architecture to an open architecture, where you have a standard hardware, because merchant silicon became very popular. People moved away from custom silicon to merchant silicon, and that gave rise to white box switches. And there was wide adoption with cloud providers, etc., and that popularized the white box switches being used. There was a lot of innovation that gave rise to smaller form factor switches, single switches, people moving away from chassis to single one-use switches, which give you more performance, which reduce the hardware footprint, which reduce the power and cooling requirements in a data center. That was one of the key innovations of moving in that direction. And evolution of spine and leaf claw-space architectures that came in. It also gave rise to an community like the Open Compute Open Compute project, which actually allowed for people to actually, vendors like Facebook, etc., to come back and share their experiences in their data center with the different open communities, so that everybody could learn a little from what their experiences in the data center has been. And that, in the Open Compute OCP, was a forum which allowed us to do that. They ventured on different initiatives. One was to disaggregate the hardware and software, where they actually went ahead and developed ONIE, which was the thin bootloader that gets preloaded on a lot of the open networking vendor switches, which allows the hardware to then support different operating systems. That was a big innovation in networking, where you see the hardware and software being disaggregated. So that is Open Networking 1.0. Then we talked about automation. There are different operating systems using different ways to configure the network. Some take a box-by-box approach, some have a fabric manager approach, or you can take a DevOps approach, which has Puppet, Chef, and Ansible as the configuration layer and automation layer, and then you can use other orchestration tools to bring it all together in a network. Then we talked about how these different operating system vendors got consolidated into bigger companies with the market changing, and some of them went back to a proprietary model again. And that is where the emergence of SONiC became important, because SONiC is a community-driven network operating system. It is widely adopted in, it was popularized by Microsoft. The Azure cloud of Microsoft has like 40,000 switches running on SONiC. That is one of the largest references for SONiC. There are other large vendors adopting SONiC, like Comcast and many others, and there is a session on SONiC, and I'll talk more about it. But that is something that is exciting, because that is Open Networking 2.0, where there is no fear that the operating system is going to be, taken back into, will get acquired and go back into a company, and they'll follow a proprietary approach again. That is the promise of SONiC. That is an open community-driven operating system. You have all the mainstream networking vendors contributing code to that. And Dell has gone one step ahead and actually announced the release of an enterprise version of SONiC that will, that means there will be support wrapped around it. There will be, Dell will ensure that there are bug fixes and there is quality assurance on the, on the operating system, so that people don't have to, rely on a community for support. You have a vendor that will support it. Just like what happened in Linux, you had Linux, which is an open community-based operating system. But then Red Hat went ahead and offered the support wrapper around it and popularized it by giving it the enterprise level of support. And that is what Dell is doing with SONiC. So that is what I discussed today. So open networking, SDN, the automation approaches in SDN, which is fabric-based, DevOps-based, etc. So I think I have 3 minutes more. If there are no more questions, we can wrap up, but I'll just wait, for 2 minutes. I've already done a quick recap. And before I close, I also want to thank TRA, who is the sponsor for this, who has enabled us to actually given us an opportunity to actually come here and present technology to a wider audience. I really have to thank them to make this, for having made this, given us this opportunity and created this platform that is wonderful, where different people from the industry can come and talk about technology and make it more popular and simpler for people to understand. So I think this is a great initiative from Telecommunications Regulatory Authority, TRA. Like to really thank them and for this great work, and I hope they continue doing this, so people get to hear more about technology broken down in a simple way, so that everybody can understand, what are the latest trends and what is happening in the industry. So with that, I'm at the top of the hour. It is 11:59, and we have a hard stop at 12. So thank you so much, and have a wonderful day. Thank you.